This is the first part of lecture today, so it actually kills the recording when we go to breakout sessions, so I have to remember to redo the recording every time. Okay, so, all right, so Kaiten, let me know if you got the same thing, okay? Because I know this is gonna be a little tough for some of us. Jacob, did you finish this one?
Not quite yet.
Okay, Idali, what about you?
Yeah, but I don't know if it's right.
Okay, Symphony, what about you? Symphony, are you there? You're almost done? Okay, so I'm just gonna go through the solution to this because I don't want us to spend like all class on this problem, but it's also a really good problem that we're gonna have to, the type of which we're gonna have to come back to. So more on that later. All right, so we've got this situation here, right? Where we've got to turn all of this somehow into CH4 plus O2 yields CH3OH. And the only way to balance the oxygens in that equation is to multiply by 2 there and there, okay? So that's a balanced chemical equation because what we're doing is we're forming methanol from methane and oxygen, okay? Methane, oxygen, methanol, okay? So how do we combine these equations up top to get that equation at the bottom, right? And what in the world is delta H? So delta H for this reaction equals what, right? Okay, so here's what we do. We look at the carbon situation, and we've got to have 2 methanes on the left and 2 methanols on the right. So we're going to have to multiply this guy by 2 and this guy by 2. And I'm going to put parentheses around the entire equation, treating enthalpy as a stoichiometric product, okay? And then the bottom reaction doesn't necessarily have to be multiplied. Let's see if things will cancel out as they are. So right now you've got let's see, you've got 2 times 3 H2s, that's 6 H2s, and then you've got 4 H2s here because it's 2 times 2, and then 2 H2s there. So actually, yes, those hydrogens balance, they cancel out. Then you've got 2 waters here, so H2O times 2 in the outside the parentheses, and then you've got 2 waters here. Those are going to cancel. Then you've got 2 carbon monoxides here because you're multiplying CO by 2. And then here's 2 carbon monoxides also. Those cancel as well. So what do you get when all this is said and done? You do get 2 times CH4, 2 times methanol, and 1 times O2. And in fact, that's our equation down below. Okay, so how do we make sense of the enthalpy situation? All right, so really it's just 2 times this, right? So 2 times that guy, and then you've got 2 times this guy, and then you got 1 times this guy, okay? And you just add them up. So 2 times 206 is 412. 2 times negative 128 is negative 256. So 412 minus 256 is 212 minus 56 is 260. 2 minus 6 is 250. Sorry, no, 160. Doggone it. 162 minus 6 is 154. So that's positive 154. And then you do this guy here, plus negative 484. So 154 and 484, that's going to be negative 330. Okay, so negative 330, but you've only got 1 methanol. So it asks you per one mole of methanol. So your overall delta H for the whole reaction is negative 330 kilojoules, which implies negative 165 kilojoules per CH3OH. All right, now I did all that math in my head, right? So 400 minus 250 is 150, and then you've got minus 500 is going to be, or negative 3. Yes, that should be about right, actually. So I think that math is correct. So how did I do on the math, and does anybody agree or disagree or have any questions? So I'm looking at the math.
I got negative 164, so like the same thing
Okay.
as yours.
Perfect, yeah, so I'm sure your answer is more accurate than mine. Okay, very good, Italy. All right, so I want to open this up. So, Kaiten, what did you get? Is this the same answer you got? You said you were almost done.
Yeah.
Okay, good.
Yeah.
And
So
what about?
I got that answer.
Okay, and what about Jacob?
Okay.
Is this what you got roughly? Okay, welcome, Cindy. I can mark you present now. Okay, what you were having trouble connecting?
Yeah, my Wi-Fi went down and my mom had to call Cox so they could turn it back on.
Okay, that's crazy. All right, well, welcome back.
I've got a.
All right, so what's your question, Kaiten? What's your statement or question?
So this is a notation thing. What's the difference between delta H with the degree superscript as opposed to just delta H? Because I remember there being a difference. Is
Oh.
it something about like standard state?
Yeah, I think the not implies standard state. Yep.
Okay.
The delta H with that degree symbol implies standard state.
Okay.
Yep. Yeah. Yeah. Okay. All right. Okay. So, okay, Marcella, does this make sense or do you have questions? Can't hear you.
Not, I mean, kind of confused, but that's fine.
Okay. So you were saying yesterday that you want to see more. Okay. And then Shifa, before you guys take off, Shifa and Mercedes, how is this going? Does this make sense to you or do you have questions?
I understand like the general idea of it. It's just when I start like trying to put it in by myself, I get confused and stuck. But then once you go over it, like I understand it. It's just I have a hard time completing it on my own.
Okay, and we'll get there. Okay, April, how are you doing?
I get it, but I have a hard time with when I'm supposed to what number I'm supposed to multiply sometimes.
Okay. It just takes practice and experience. I don't know if I have like a good, I'm kind of narrating you through my thought process, but I don't know. Like, I know for sure when I was your age, this didn't look as obvious to me as it looks now. And I think it's just because I've had this information in my brain for so long, it's chunked itself. And so I don't have to spend as much local memory or like short-term memory or active working memory thinking about this stuff. I just say, oh, okay, I got to do this and that and the other thing. And so I'm going to try to pass as much of that on as I can. But that comes in like the solutions on the lecture. So I would recommend replaying the video and kind of watching how I think through it, because I think that'll help you learn to think that way too.
All right.
Okay, and more practice also will help. Okay, so any questions for me before I move on to the next problem?
The next one's going to be one like this, right?
No, we'll see some more like this at the end of the chapter, but we're going to move on to a different problem type right now.
Okay, then never mind.
Okay. I mean, it's not going to look entirely foreign, but it's not going to look exactly like this either. Okay, I'm going to erase the board. And then let's take a look at this next one. So example 7.10. So calculating the heat output of a fuel. Okay, so with this heat output calculation business, what you're doing is you're basically just treating delta H as a stoichiometric product. Okay, so you're just treating it as a product of the reaction. So this one says, how much butane should a backpacker carry? Calculate the mass of butane that you would need to burn in order to obtain 350 kilojoules of heat, which is just enough energy to heat 1 liter of water from 17 degrees C to boiling at sea level, if we ignore all heat losses. Okay, so you're going to need more heat than that. I'd say about 3 times as much, but at least maybe let's call it 4 times as much. But let's go with this equation. So 2 butane plus 13 oxygen give us 8 carbon dioxide and 10 H2O, and the delta H is negative 5,756 kilojoules. Okay, and you only want 350 kilojoules, right? So what do you do in this case? So you want to calculate the amount of mass of butane that you're going to need to burn. So this is really just a stoichiometric problem. This is almost like one of those unit conversion problems that we did early in the year. But I want to hear from everybody, how many of us want to try this on our own? And how many of us kind of see how this goes, or see how we would go about this? Or how many of us want me to go ahead and lead through this first example here?
Lead through it.
Can you please lead through it?
Okay, so some of us say lead through, some of us say on our own. Here's what we're going to do. I'm going to set my timer for 5 minutes. If you want to work on this on your own, that's fine. Just kind of like ignore what I'm doing at the board. Otherwise, and you can even mute your audio output, but I'm probably going to start back up. So I'm going to set it for 3 minutes. Okay, so let's go with, sorry, still getting used to it. 4 minutes. Okay, 4 minutes. So mute your output and I'll take the group through it. Okay, so we're going to set the timer for 4 minutes. Hey Siri, set timer for 4 minutes.
Okay.
All right.
4 minutes and counting.
Okay, so what's going on here? So, okay, we want to obtain 350 kilojoules of heat, right? And this reaction puts out negative 5,756 kilojoules of heat. Okay. So, all right, so our real question is how many moles of butane are we going to have to burn? Or what it actually says is the mass of butane in grams. Okay, so we're looking for a gram amount. Okay, so we want to know how many grams, right? So we start with 2 moles of butane. So we've got, well, that's how many moles of butane there are in the reaction, but we actually start with 350 kilojoules of heat. So we say to ourselves like this, 350 kilojoules, okay, per, we don't know how many grams of butane, okay, but times 2 moles butane per negative, and we want, they're all negative, so it's per negative 5,756 kilojoules released, okay, because your stoichiometric amount here is 2 moles of butane. So 2 moles of butane combusted produce exactly this much heat output, okay, times some number of grams. So it's going to be 12 times 4 is 48, plus 10 is 58. So 58 grams butane per 1 mole butane. Okay, and now we're actually going to get our answer, right? We want grams of butane. So kilojoules cancel out, and then moles of butane cancel out, and we're going to get grams of butane as our answer. So if we do this out mathematically, we get negative 700 over that, which actually isn't bad. That's going to be about 1/8, and if you divide 58 by 8, you get about 7. Yeah, so you're going to get approximately 7 grams of butane. Okay, you get right around 7 grams of butane. Okay, so that's how that math works out. So I want to open up the floor. We've still got a minute before those who are working independently are going to chime in. So I just want to open up the floor to questions. So who's got a question about how this problem works? No one? No one have a question? April, how are you feeling about this?
I got it.
You got it. Okay. And then what about Ryan? Ryan, how do you feel about this question? Ryan, you're good? Okay. And then what about Brianna? Brianna, does it make sense to you?
Yeah, that just doesn't make sense when I do it on my own. Like when I hear you explain it, I'm like, oh, that makes perfect sense. Like, why didn't I think of that?
We'll have plenty of time once you guys start doing practice problems out of the back of the book, out of the end of the chapter. These chapter problems, don't let it bother you if you need more help, because you're seeing them for the first time. Okay, once you get to the end of the chapter, that's when you should expect yourself to have internalized these lessons and learned enough to be able to apply what you've learned. Okay. Okay, that's a cute wall. It says hugs not drugs. That's cool. I really miss you guys. This is tough. This whole like being, stuck at home or whatever, like that's not normal. Can't wait to get back to school whenever that happens. Okay, so 3, 2, 1 here. Okay, so timer's done, and so like Kaiten and Symphony, just want to welcome you guys back. Jacob, welcome you back. So guys, are we all good with 7 grams of butane as the answer for this problem? Okay, and that is, who's at the top there of my screen? No, that's Idali. Okay, Idali, you're good. Kaiten, are you good with this being 7 grams here? Is that what you
Are you talking to me?
Yeah, is that what you got, 7 grams? Yes? You're muted, so I can't hear.
Yeah, I got 7 grams.
Okay, cool. Symphony, you too? Perfect. Okay. Antonio, how are you doing?
I'm good.
You doing well?
Yeah.
Okay, great. Okay, so I'm going to go ahead and erase this board, and we'll move to our next problem for the day. So next problem is this one, 7.14a. Okay. So the answer for the last problem is indeed 7 grams, right? And so you got to ask yourself, if we burn propane, right, are we going to need more or less? Okay, so the answer is yes. I want you to do this problem all on your own. So everybody should be able to do this on your own. And one of those who was with me last time, I'm going to ask you to present the answer. Okay, so do this one on your own. Take another 4 minutes. That's okay. Take 4 minutes and try to do this one on your own. It's very much like the last problem. Hey Siri, set timer for 4 minutes.
Okay, 4 minutes and counting.
And I'll be available by chat if anybody wants to chat me with a question or whatnot.
Wait, what page is this in the book? Like
This, I don't even know. It's 7.14a, so it's close to what we were doing last time. 7.14a. Yeah, look at page is this? 400. Okay, it's on page 400 in the book. All right, 400.
Okay, thanks.
Mm-hmm. You're welcome. Yeah, that's right, Kaiten. Good job. Mm-hmm. Good work. Yeah, Italy. That's basically what Kaiten got. Very nice. Mm-hmm. And the answer is right there too on the problem. So very good. Uh-huh. Yep, very, very good. Okay. So that's time. Okay. So Idali, will you take us through the answer to this problem, please? Just take us through how you solve this.
Okay, so first I calculated the grams for the C3H8, and that was about 44 grams.
Okay,
And then
so C3H8 implies 44 grams per mole.
Mhm.
And I'll show that a little differently. Okay, go ahead now.
and then I multiplied it by the amount of heat, the number they give you, which is 350. And that would be over the delta H, which would be the negative 2,220.
Okay, so times 44 grams. Times. Okay.
And then when you multiply the numbers out and then divide over the 2,220, you get about 6.936. So it's like 6.94.
Okay, and that's what we get. 6.94 grams. Okay, that's perfect. So kilojoules cancel, moles cancel. Okay, there we go. Okay. So that's a neatly worked solution. Okay. Scholars, any questions about that? Okay, Brianna, how'd you do on this one? Were you able to get this one on your own?
No, I got like 0.3, but I don't know. I feel like I can do it, but I'm just not getting it right.
Okay. What about you, April? Did you get this one on your own?
I didn't get it at first, but now I saw what Idali did and I get it. I kind of get it now.
Okay. All right. Jacob, how about you?
Yeah, I got it.
Okay. What about you, Ryan? Perfect. And Antonio?
Yeah, pretty good.
Good. Okay. Kaiten, you got this one too. Okay. Symphony, how about you?
Yeah, I got it.
Okay. Renisha, what about you?
I'm getting it.
You're getting it? Okay. That's cool. I'm going to go ahead and delete the screen. Or unless anybody has a question. Does somebody have a question for me about how this one works? Okay. I'll delete the screen. And then I'm going to go back to next question. So next question is self-test 7.14 B. Okay. So ethanol trapped in a gel is another common camping fuel. What mass of ethanol must be burned to supply 350 kilojoules as heat? The thermodynamical equation for combustion of ethanol is, right? And there we go. And let's just knock out the molar mass calculation right away so nobody has to worry about it. So for this one, you've got C2, that's 24, H6, that's 6, so 30, plus 16 is 46. So you got 46 grams of C2H6O, that's ethanol, per mole. Okay, I don't want you to have to get stuck on that thing. All right, so it's really a very similar calculation to the ones that we've just done, okay? And let's just take another 4 minutes and knock this out. I want everybody who's kind of been struggling with these last two to really get this one, okay? So hey Siri, set timer for 4 minutes. Hey Siri, set timer for 4 minutes. Okay.
Your timer is set for 4 minutes.
All right, and somebody just chatted me. I'm gonna check in. And I'm here, guys, if you have questions that you'd like to ask over the chat. Okay, so Caiten's got his answer. Let's check. Yeah, that sounds about right, Caiten, because the delta H is about half. So that looks good to me. And the mass is about the same. So this one over that is 1, 2, 3, 4, so 1/4 times that. Yeah, that's exactly what I would say. Yep, yep. I would ballpark it right there. Very good, Caiten. Very good. Yeah, that's exactly right, Idali. That's what I got. Good job. It's good to stretch. Okay. And then if you want to chat me your answer, I can tell you whether it's correct, okay? So if you feel like you have finished the problem and you want to just send your answer to me, I'll weigh in. Yeah, that's what I got, Antonio. Very good. Uh-huh. Yep. April. Yeah, that's right. Except your mass amount must always be positive, okay? So you want the positive sign. Symphony, very good. Uh-huh. Yep. Good job, guys. All right, so guys, we're at the 1.5 minute mark, okay? So Brianna, how are you doing on this one?
I was just about to send you my answer.
Awesome. See, that's what I'm talking about. Very good. Okay. Jacob, you got this?
Yeah, I was also about to send you my answer.
1428. Perfect. Okay, Brianna, perfect. Very good. Yep, very, very good. Okay. Jacob, your number's just a little bit off of ours. I think there's probably some rounding error there or something.
Yeah, I rounded a little bit.
Okay. So really, this one comes down to like, okay. So Brianna's good. And then, okay, April, how did you do? Did you get this one already?
Yeah, I got it.
Okay. April, why don't you present your answer, okay? And I'll be your hands at the board here.
Okay, so you already have the 46 grams of C2H2O. So
Yep.
you're going to multiply that by 350.
Okay, so what I would do is if it's okay with you, I'm just going to start with the number they give us. So I'm going to start with 350 kilojoules, if that's okay, because that's one number. It's
And
kind of my old school habit of doing them this way. But okay, so you start with that, and you want to multiply that by your conversion factor.
Yes.
Okay, that's fine. I'm just going to shorten that to grams per mole because we all know we're talking about ethanol. Okay, and then what's next?
And then you multiply 1 mole over 1,368.
And Jacob, is that what you got? Is that basically what you did in terms of steps?
Yeah.
Okay, then there's just some rounding error. Okay, and then what'd you get, April?
I got 11.7.
11.7, okay, kilojoules. That's not kilojoules, grams. Okay. Okay, perfect. All right, so you got 11.7 grams. Okay, yeah, that's basically what I got. I looked at it and I was like, okay, 350 divided by 1368, that's about a fourth, and 1/4 of 46 is about 1/4 of 48, so that's about 12. So I just ballparked it at 12. So you guys with your extra decimal point, you're looking great. Okay, so nice job, scholars. Okay, so anybody have any questions for me about this problem? Okay, so I'm really happy, right? Like we're figuring this out, and that's really, really important. Okay, we've gone through a series of like 3 problems now that are pretty similar, and so all of us are up to speed. And so that's what really matters to me because we should all be able to do these. So that's really, really good. Okay, so I'm going to go ahead and crush this. We should all be able to do every single problem. There's nothing in here that's beyond our ability to comprehend. Okay, so next one. Okay, so I'm going to show you a little resource, right? Okay, so first off, I feel like, is it just me or are we getting through problems faster with this format?
We're getting through faster.
Yeah, this is like a lot clearer, right? Like I'm not writing over text, etc., and like we're just like moving right along. Yeah. Okay. Okay. Where was this all year? Okay. So yeah, I think this is really, really good. So all right. So this is some stuff that we need to know. So basically, from your textbook says that delta H naught equals the sum of the delta F naught for the products minus the sum of the delta F naught for the reactants, right? So what the heck is that? So that means that you can find reaction enthalpies from the enthalpies of formation for any given chemical. And the enthalpy of formation is just the enthalpy of the reaction that would put together the compound from its component elements, okay, at standard state, okay? So that's what we're dealing with there. And I know that sounds kind of complicated, but it's in your book. And if you have questions about that definition and you'd like to go over them further, we can talk about that during office hours today. So I'm available at 3:25. And yesterday, Antonio and Caton stopped by and we just had a nice rap session about reaction rates and chemical kinetics. So I really enjoyed that. So the more you guys can stop by for office hours, the happier I will be for sure. Okay, so here are some standard enthalpies of formation, right, in kilojoules per mole, and these are for a few different chemicals, right? And we're going to see one of them in a little bit. We're going to see glucose, okay? So it actually just gives you the glucose enthalpy of formation, right, which is kind of crazy. So your self-test on this is to calculate the standard enthalpy of combustion of glucose from the standard enthalpies of formation in tables 7.5 and appendix 2A. Okay, so this is really just an extension of what we've been doing. Let me go ahead and look all that stuff up. So, oh man, this is like brutal. Okay, so glucose, oh, golly, glucose, enthalpy of combustion. So you're combining glucose with oxygen to form carbon dioxide and water. So let me just see if I can just Google this stuff. So, sorry, this is brutal. Okay, so, okay. So enthalpy of formation of carbon dioxide is negative 393.5 kilojoules per mole. So I'm going to put that on the board. So carbon dioxide, to form carbon dioxide, you're going to have carbon plus O2 yields CO2, and delta H equals negative 394 kilojoules for that reaction, okay? That's balanced. And then you're gonna form with oxygen. So oxygen's enthalpy formation, okay? So O2 delta H of formation at standard state, that's defined as 0. Okay, any element's enthalpy of formation is defined as 0. Okay, you just have to know that. And then you're forming CO2, so CH blah 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 plus O2, and you want the enthalpy of combustion. Okay, and they give you one more thing. Okay, they give you one more thing. So they give you in the problem. I'm gonna go. There we go. I'm gonna go back over here. They give you that glucose has an enthalpy of formation of negative 1268 kilojoules per mole. So you just have that. So that's the enthalpy of formation of that thing. But you want the enthalpy of combustion of this thing. That's the enthalpy of formation. Okay, so it's, oh gosh. Okay, so that's the enthalpy of formation. What are we supposed to do with this problem? We're supposed to find the enthalpy of formation of combustion from enthalpies of formation. Okay. So you're going to go from glucose to carbon dioxide and water. Oh, we have to have the enthalpy of formation of water. So
Dr. J, it's given on the table there.
It's on the table. Enthalpy of formation of water. Oh, and they had carbon dioxide too. Okay. So water is, thanks, Caton. Water liquid is negative 286. So you've got, man, yeah, that's just going to be ugly if you try to do this that way. So I'm actually going to erase this. So let's just do it the other way. So I'm going to go back to, okay, so what was carbon dioxide? That was negative 394. Okay, So let's go back to the other, and then water is negative 286. Okay, so delta HF for H2O equals, what was it, negative 286? Negative 286, yeah. And then it's negative 394. Okay, negative 286. So you have to actually draw it all out. Kilojoules per mole. And then delta H formation of CO2 equals negative 394 kilojoules per mole. And then delta H of formation of glucose, which is the other one we need to know, was like negative 1200. So it's negative 1268. So negative 1268. Okay, so that's glucose. And okay, glucose. Okay, all right. All right, so, okay, so what's the scoop here? All right, so you've actually, so this is the combustion of glucose, right? So what you have here is you have, and then just really quickly, delta H of formation of O2 equals 0 kilojoules per mole. Okay, and these are all its standard state. Okay, all right, so what's happening here? So you're combusting glucose, right? So you've got C6, H12, O6 plus some number of oxygen molecules gives you some number of CO2 molecules plus some number of water molecules. Okay, and this is a really important reaction because this is the metabolic reaction that gives us the energy that we need to do what we do. So the bulk of our energy that our cells use on a daily basis is derived from glucose metabolism. So, all right, so what's happening here, right? So let's see if we can balance the carbons. So it's 6 on the left, 6 on the right. And then you'd have, and the balanced chemical equation is going to matter, so I'll show you in a second. So 6 on the left, 6 on the right, and then H2s. So you've got 12 on the left, so we got to have 12 on the right. So we're going to have a 6 in front of this guy. So 6 times 2 is 12. And then O6 on the left plus how many oxygens on the right? So you got, with this one, you've got 6 times 2 is 12, plus 6 is 18. 18 oxygens on the right, but you've only got 8 on the left so far. So you got to have 6 plus 12, okay? So to multiply this guy by 6. All right, now that should be correct. Let's double check. So 6 carbons, check. Carbons are good. Okay, and then what else? Okay, so 6 carbons and 6 carbons. And then we got 12 hydrogens and 12 hydrogens. That's good. So 12 and 6 times 2 is 12. Then we've got 6 plus 12 is 18 oxygens, and 12 here plus 6 is 18 oxygens. Yeah, so that equation's balanced. Okay, and why was I so careful about balancing that equation? It turns out if I don't balance that equation, we are in trouble, okay? Because we've got to multiply like all these heats of formation by the number of each molecule that we have there, okay? So we subtract the reactant heat of formation from the product heat of formation. So how do we do this? So we have our delta HF for H2O, right? So that's negative 286. So here's what you do. You go negative 286 okay? You multiply that bad boy times 6. And you got CO2, negative 394. You multiply that bad boy by 6 also because you got 6 of those. And you're going to add those two together, okay? And then you've got glucose, which is negative 1268, and there's only one of them. And you got O2, which is 0. Okay. So what's the heat of combustion? So the heat of combustion is this sum over here minus this sum over here, you're going to add these two. Okay, so this on the right minus what's on the left. So you wind up with, if you add all that together, let's just do the round number math. So you got like 6 times 3 is 1800, and you got 6 times 4 is 2400. 2400 plus 1800, let's round it off. Let's call that 4,000. So negative 4,000 kilojoules. Okay, and then on the left side, you've got negative, so that minus, so you have to add, you have to do a plus, okay, 1268, so let's call it 1,300 kilojoules. Okay, that's going to give us roughly 2,700 kilojoules. Okay, that should be our answer, 2,700 kilojoules. Okay, that's an ugly 2,700. So I just got to chat. I wonder if I botched a calculation somewhere. Did old Dr. J make a mistake? Okay, yeah, okay. Nice. Okay, nice. Okay, so Caton got 2,800 kilojoules. He says final answer. Okay, I'm taking that as confirmation that I'm good to go. Caton's a pretty solid performer here. All right. So okay, so that was how that problem was done. Woof. Okay, so that's a lot, right? Like that's just new for you, so you haven't seen that before. But it's actually a really simple way of calculating reaction enthalpy. All you got to do is get the balanced chemical equation and then multiply each chemical by its heat of formation, and then, or enthalpy of formation, which we call heat of formation, then subtract the sum of the reactants from the sum of the products, okay? And when I say sum, I'm talking about sum of heats of formation, okay. Whew. Okay, so that was a little bit. So I want us to start sharing out with questions right now. So what are your questions, and how can I be of assistance? I'm like putting my big screen back up so I can see everybody. So what are your questions, and what can I do to help? Because that was a fairly lengthy procedure, even though it was actually really straightforward. Okay, Brianna, could you start us off with a question?
Hello. I'm okay, I think.
That made sense to you?
Yeah, it makes sense, but it just looks like it's going to be more difficult to execute.
Yeah, it's actually pretty simple. Like this was always my favorite way to go about it because it was so straightforward, even though there seemed to be more steps. Like I never had to like figure out how to combine two chemical equations to get the final chemical equation that I wanted. I was always just like, oh, okay, I add all these together on one side and then I subtract, you know, these other ones added together on the other side and I'm done. Okay. Sinead, Sinead, any questions?
No, like Bree said, like I get it, but it looks like it would be hard once we start practicing it. But
Okay, so we just need practice. Okay, but it makes sense. April, you two make sense?
Yeah, I got it.
Okay. Rainisha, how about you?
I got it. It's making sense.
Okay. Idali, Jacob, Caton, Antonio, Ryan, how are we doing?
I'm good.
I'm feeling pretty good
here.
Okay. Yeah, and Caton, I got the same answer you did. I rounded to 2,700, so I'm calling your 2,800 spot on. Okay, so I'm gonna go ahead and clear the screen, and then I'm gonna get a new problem up for you. Just give me a couple seconds here because it takes me a little while to copy paste. So we're actually making really good progress here. So let's end with one more of these little enthalpy problems. So that was 7.15a. Let's see if 7.15b is gonna work. Oh yeah, this is fun. Oh yeah, so Caton, you got it right. That was the answer. 2808 is what they had. So I'm feeling pretty good. Okay, so diamond from the information in Appendix 2. Enthalpy of combustion of diamonds. Okay, this really isn't so bad. So this is one of those things that you can do. You can actually burn a diamond. Guys, did we watch the diamond burning video?
no.
I don't think so.
Oh
You
my
mentioned it once. It had something to do with like liquid oxygen.
Oh yeah, you can burn a diamond in liquid oxygen. It's mad cool. Okay, so like let's just watch that right now. Like life's short. Like we can't be like not watching these things. So let me bust out.
Oh, this takes me back to Ethos Lab.
So like let's go. Okay, so let's go here, and we're gonna go. Close that. I don't know what this is. Okay, so let's go to. So we can pick up with this one tomorrow. So let's just watch this video. Like, I'll show you this. If we don't do another problem today, that's okay. We're basically done with this chapter. So we have to have a discussion about like what we're going to do over break to review and what the AP test is going to look like and when we're going to take it. But okay, so this was pretty cool. Let's watch this. So it's like a 4-minute video. It's totally worth watching. So okay, so we're gonna worry about that problem next time. We're gonna watch this this video today because that's fun. So you can actually like burn a diamond, and so that's what we're gonna look at next. We're gonna actually, our first problem for tomorrow is gonna be, first thing we're gonna review the combustion of glucose from enthalpies of formation. Second, we're gonna go ahead and look at the combustion of diamond. We'll figure that out.
I don't suppose, by the way, I mean, you very kindly lent us your gold, but I don't suppose you have a spare diamond on you, do you?
Well, I don't myself, but my wife actually has one.
Aha!
You don't want to take that as well, do you?
Well, it's all right. It's all right.
I get it back.
Thank you, Mrs. Croto. Of course, yes, you can trust me. All right. Okay, this is beautiful ring here. It's sort of an engagement ring or something. It's really quite lovely. It's the diamond comes out quite easily, doesn't it? Yes. But we can see it more clearly now, though. So can't we look at that? This is beautiful. What a beautiful diamond. So it is a real diamond, though, is it?
It's as real as you can get.
Oh, it's quite stunning. So, but of course, we want to show that this graphite is made up of carbon. And there's one way we can do this. We can burn our carbon in oxygen, and we'll get, what will we get?
Carbon dioxide.
Carbon dioxide, see, it's pretty good. Yep, carbon dioxide, yes. And then if we bubble that through lime water.
Oh, calcium carbonate.
Calcium carbonate, that's the test for carbon dioxide, of course. And it'll be white. Oh, I didn't ask you that one. Yeah, no, just getting carried away now. All right. Anyway, let's just see this over here. So we have some apparatus, and this is where we're going to burn some graphite, all right, and show that it is made of carbon. So what's bubbling through here is just oxygen. This won't react with our lime water at all. Okay, and we're going to see if we can light the graphite and get it burning inside the oxygen. And, there we are. Thank you, that's great. So now we have a hydrogen flame. So this won't produce anything, it's only going to produce water. You can see the water just beginning to condense. Beautiful, I'm going to turn the flame off. Look at that, what do you think?
It's brilliant.
I think it is literally brilliant, yes. This is the carbon combining with the oxygen that's flowing through here, and hopefully we're going to see this changing colour, giving us the milky colour, showing that there's carbon dioxide present. I mean, I think we should test diamond as well, don't you? What do you think? Yes? Does Mrs. Croto mind?
Okay.
Okay, in the name of science, well, that's very kind of you. Harry seems a little nervous. I'm sure it is a real diamond.
Well, I think it's real diamond, yes, I'm sure.
Well, actually, let's give it a go then. So we'll just put it on there, and again, we'll put this on here. Right, so we have our flame. Here we go. The moment of truth. Now, can we get our diamond to burn in the oxygen? Oh, look at that.
I hope you can afford to pay for this.
Well, the good news is, Harry, it is a real diamond. Okay? I think this is absolutely stunning. I mean, that diamond there is, it is burning in oxygen. It's combining with the oxygen of the air. Have you ever seen a diamond burning like that before?
No, I haven't.
No, it is quite stunning to see, isn't it? And remember, there are no flames coming from this. So this is just, again, the heat of the reaction as the carbon combines with the oxygen that's present flowing through here, forming carbon dioxide. Oh, that is absolutely stunning. Just look at that. It's glowing all by itself. It's absolutely brilliant. I think that's amazing. And look, our lime water is going milky.
It's the most expensive lime water I've ever seen, man.
Actually, I think you're probably right there. It really is the most expensive lime water that you've ever seen. But I think we should come clean. Don't worry, we didn't destroy Mrs. Croto's engagement ring. I mean, that really would be quite harsh. This it's a pretty low-grade diamond. It still looks pretty good to the naked eye, but actually the experts say it's not very valuable at all. But it is a real diamond, and it is combining with the oxygen here, and I think that's a pretty stunning reaction. So thank you, Professor Croto, for coming in. It's a real privilege to have a Nobel Prize winner here helping out with an experiment. Thank you very much. Thank you.
Okay,
The
so
whole time I thought he just burned this lady's ring, and I was like, oh no.
yeah, so what did you guys think of that experiment? Pretty cool, or you have questions? We should do that. If I had a low-grade diamond, I would totally light it up like that. That'd be so much fun. Yeah, okay. All right, so guys, the reading assignment for tonight is going to be short. It's just section 7.20, but I'll remember to put that up. So section 7.20, and then we'll start doing, we'll go through all of that, as well as this problem that we have for diamond combustion. And then we'll do some end of chapter problems tomorrow and on Thursday. And then we'll also talk, definitely no later than Thursday, about what we're going to do over break and about the AP test, okay? So, yeah, so that's the deal, okay? Okay.
See you later, Dr. J.
All right, guys, you have a great afternoon, okay? Wash your hands, stay safe, try to get some exercise.
All right,
will do.
Bye, Dr. J.
Bye, guys.